Hi everyone, my name is Alexey Naiden and I'm a staff engineer at TaxCare. What we do as a company is we provide security patches for end-of-life open source software across a variety of languages, including Java, of course, which means we fork upstream repositories, backport patches from modern versions to the end-of-life ones, and release fixed versions into our private repositories. And my job specifically is to automate this process as much as possible. And my talk today is about practical lessons that we learned when we were building tools that encapsulate both AI and deterministic code. So lessons or patterns that can be applied to make sure you don't just get a cool demo with AI or a single successful execution, but rather systematic, successful results. And before I talk about the patterns, the problem we were solving is project onboarding. So before we can start shipping patches for a project version, we have to fork the repository into our internal GitLab instance, figure out the build, understand how the tests are run, make sure they're all green, and capture this knowledge in a file that we call TaxCare YAML. So you can see example on the slide. The details are not important. I just wanted to show you the structure. So it has the Docker image, the commands and the flags required, and some other metadata such as how we upgrade dependencies automatically if we want to bump their versions up. So the issue is that if you have worked with legacy projects, especially with Java legacy projects, you probably know the pain. So some projects depend on build plugins that are no longer available, or they have some undocumented build steps, or they might have some quirks that show up after a third failure. So basically, onboarding takes several hours from a human engineer to run all the tests, understand the failures, maybe fix, and produce this taxcare.yaml file for us, which obviously doesn't scale. And this approach, this task is where we wanted to apply AI. It was very tempting because it can analyze the files, figure out the build, make any required adjustments, and save us a lot of time. So we made a bet to hand the agent an arbitrary Java repository and tell it, come back when deploy is green. And this actually worked, but getting there meant solving problems nobody warned us about. And as I said, there will be three practical patterns: containment, liveness, and prompts as source code that we have applied and we think are a good approach to dealing with a combination of AI and non-AI solutions. The first pattern is containment. A naive approach to the task that I've just described would be to ask agent to handle everything, to figure out the build, clone, repository, make sure the tests are green, and commit, create a merge request, and stuff like that. So this is a great way to get unpredictable results. Because AI forgets to commit some files, or it can commit something extra. It may try to create a pull request to the upstream repository, the public one, instead of our internal. It might create a temporary Nexus repository for deployment tests and forget to clean it up. And it can also disable tests and say, now the build is green, I'm done. And all these things have actually happened in our experience. And also, giving agents all these tasks is just fairly expensive. So instead of doing this, we built a pipeline. So this pipeline is, we have a CLI tool, internal CLI tool, that has 18 steps. And only one of them, it's the red one in the middle, uses AI. Everything else is completely deterministic. So we create repositories, branches, boilerplate CI configuration. We detect whether it's a Maven or Gradle build with deterministic code. Then we run validations afterwards. We do artifact discovery and submit merge requests, all with deterministic code. And only the steps that require AI, the only step that requires AI is compile, test, package, and deploy. So we ask AI to figure out what parameters are needed and what changes are required to make sure we can build the project. And this framing I think matters a lot. The framing that AI is not your system. AI is just a single flaky and non-deterministic tool within a usual engineering workflow. And once you start thinking about AI in this way, you immediately realize that your engineering instincts and discipline are applicable here. So you can think of retries, validation, timeouts, error recovery, stuff like that. So it works for AI as well as for everything else. In addition to this pipeline sandwich where we had AI in the middle, we also set up our code to write the onboarding results. So it's just a structured JSON that is owned by the pipeline, the onboarding pipeline, which it extends progressively as it completes step after step. And this type of file, this type of output gives us traceability. So if something fails, we can analyze what went wrong, where AI deteriorated, or maybe something else was down, maybe GitHub was down, as it happens these days. And we can even recover and sometimes continue from the failure because we persist partial results. So summarizing this first pattern, containment, I would say that don't let AI lead the work, but instead build the harness around the AI and make sure this harness takes care of validations, cleanup, and all other steps that you would normally do in any pipeline. The second pattern is liveness. And before I explain liveness, I will tell you how we got into the situation where it became important. So again, a naive approach to the task of figuring out how to do compile, test, package, and deploy steps is to ask a single AI to do everything in a single session, which doesn't work well because a lot of logs get injected in the session, failures, results, thinking process, so AI gets huge context, and it gets lost into this context. So it starts doing funny things, it forgets what it was doing, and so on. So a typical problem with agents is context pollution. And the typical solution is to split task among orchestrators and sub-agents. That's what we did. So our main agent just starts an agent for analysis that looks at the build rules, maybe reads readme.txt, or Travis ci.yaml, then the compile, test, and all other sub-agents. They get very limited context. They get one task, and they try to do this one task well. This really helps with context pollution, but then we hit another problem. So all these agents, they report back to the orchestrator when done. And another problem that we had is so we used Cloud Agents SDK, and this SDK has a limitation or an issue. If an agent tries to send more than 1 megabyte data to another agent, so orchestrator to a sub-agent or vice versa, the SDK crashes. So it's just crash. Because our agent session lives within a pipeline, the containment pattern that I mentioned, we can salvage the results, we can kind of recover, and maybe restart next time. But it doesn't address the core problem. Yeah, that agents, for example, an agent tries to send the full Maven log to the orchestrator in case of a failure, for the orchestrator to decide something. So instead of, to prevent this, we set up our agents to only report final results in a few sentences. So agent does work and replies to the orchestrator, this is done, or this has failed with this error. And that's it. And we solved this problem, but this is where the liveness issue comes into play. Now, if an agent is waiting for a long build, or is running the tests, or maybe it's thinking through a failure, human operator sees nothing. And people start thinking that the pipeline is frozen, or if it's a CLI tool running on the developer's machine, that it's stuck, and the CI kills good sessions at 39:59. So liveness is a real problem in this scenario, and we addressed it with two mechanisms. One is a heartbeat. So our harness monitors agents that they're running, and if the agents have nothing to say yet, if they're alive but busy, harness emits this. You can see the last line still running 12 minutes phase deploy. So it emits basically heartbeat markers, mostly for humans, so you can see that your pipeline is alive. You just don't want to pollute the context with status reports if it takes a few hours. And in addition to this, you can see these phase markers that agents emit: onboard analysis, onboard compile, and some others. So again, we set up our agents so that instead of doing full reports or instead of reporting in plain text or JSON, they use this partially structured output. So we can, Harness can parse the markers, the tokens, using regular expressions. And humans can just read this log and immediately see what's going on and where we are. In addition to that, another agent can analyze such logs. So when we want to run a meta-analysis on multiple onboarding sessions, we can just analyze this type of logs instead of JSON files or full transcripts, which are way larger. So the summary here is that we essentially invented a short DSL, which is human readable, machine readable, and AI readable at the same time. So it's short, structured, but not as structured as a JSON would be. Summarizing the liveness pattern is status reports are not a UX issue. Status reports should be part of your architecture of your system. So agents should not only report the final results, but make sure they communicate to the observers, and observers can be humans or automated tools, that they're still alive without polluting the context of the orchestrator that runs them. And final third approach is prompts as versioned code. I will start with an anti-pattern again. So sometimes prompts become tribal knowledge. So someone posts a prompt in Slack, another person does the same in an email thread, a third person copies it from Slack to a local file and adjusts, and you immediately lose history, who changed what the source of truth is, and why behavior of your model changes. So we wanted to avoid this from the very beginning, and we treat our prompts, agent definitions, and the skills, so basically everything we feed our AI with, we treat this as software assets. So they have their own repositories, the version history, a release cycle, and most importantly, any change always goes through a code review process. You can see an example of our onboarding skill. So there is not skill, it's the whole package for onboarding. There is the skill, prompts for agents, for analysis, for execution. I want to highlight the error handling.md. It's a file, essentially a playbook, where we categorize typical failures for Java projects and how agents should approach them. So if something fails, any agent reads the playbook. And project nuances is another thing. So when there is a quirk in a specific project, we store is in the nuances, and this can be reused across multiple versions of, let's say, Guava, or across projects of the same family. And why this matters a lot, why this changes the approach. So now if onboarding fails, a human reviews the logs, the onboarding result, the session logs that we saw, and it makes a commit to the project nuances, so maybe to the error handling document. This commit goes through a code review process, and then there is a new release of our AI package, which is picked up by our workflows. And now, instead of just doing the debugging and troubleshooting sessions, we have a feedback loop, which is source controlled. So summarizing all three patterns, containment, liveness, and prompts as code. So make sure your AI is controlled by your code, and you only delegate to AI tasks that require AI, and everything else is deterministic. Make sure your agents can report without polluting context, and treat your prompts as part of your software system, not as just plain text. And if I had to summarize my whole talk in a single sentence, it would be this. Don't put your code in Claude, but rather write software that encapsulates Claude. And this approach helped us to move from it just works sometimes situation to we really use it in production and can trust this onboarding process. And since that's a sponsored talk, one last sentence about TaxCare. We provide extended lifecycle support for thousands of packages in open source, and tools like this one that I've described, which combines AI where it's needed and deterministic code in all other places, is the only way we can make this sustainable at this scale. Thank you very much.